Hello. In this video I would like to explain the role of Retrieval-Augmented Generation, RAG, in multimodal AI. Multimodal AI is moving beyond systems that merely process text. Large multimodal models, LMMs, are designed to interpret and reason across images, video clips, audio recordings, documents, tables, and text. This broader capability creates a new challenge. The model must not only generate fluent answers, but also connect its reasoning to the right evidence across multiple forms of data. Retrieval-Augmented Generation, RAG, is therefore especially important for multimodal AI because it gives the model access to relevant external evidence before it generates a response. Instead of relying only on what the model learned during pre-training, a RAG-enabled multimodal system can retrieve the most relevant text passages, images, video segments, audio files, or other artifacts and use them as context for grounded reasoning. What RAG means in a multimodal AI context. Retrieval-Augmented Generation, RAG, is an architectural framework in artificial intelligence that enhances the capabilities of generative foundation models by integrating an external retrieval mechanism. It has become the standard pattern for grounding large language models, LLMs, but its importance is even greater in multimodal AI. In a multimodal context, RAG involves retrieving relevant text, images, video clips, audio recordings, or other data objects and feeding them into the context window of a large multimodal model. While traditional foundation models generate responses based solely on patterns learned during training, RAG-enabled systems first search an external database or corpus to find relevant information related to a specific query. The retrieved content is then provided as additional context to the generative model, which synthesizes the final output. This process allows multimodal AI to move from general pattern recognition to evidence-grounded reasoning. The response is not based only on the model's parametric memory, or the information encoded in its internal weights during training. It is also grounded in verifiable, up-to-date, or domain-specific evidence. This grounding significantly reduces the risk of hallucinations because the model can be prompted to reason from retrieved artifacts rather than inventing details from memory. For example, if a user asks about an event captured in a video archive, a multimodal RAG system can retrieve the relevant video segment and any associated transcript before generating an answer. If a user asks about a medical scan, the system can retrieve comparable images, notes, or prior cases to support a more evidence-based interpretation. RAG is the bridge between raw multimodal data and model reasoning. A critical challenge in modern AI is the gap between raw, unstructured multimodal data and the sophisticated understanding or reasoning capabilities of foundation models. High-resolution images, audio recordings, video streams, scanned documents, and other multimodal artifacts are rich sources of information, but they are not automatically useful to an AI model unless they can be searched, selected, and placed into the model's reasoning context. RAG acts as the functional bridge between these domains. The bridge is created by transforming raw multimodal artifacts into searchable semantic representations, often through multimodal embeddings. These embeddings allow a system to represent visual, textual, audio, and video information in ways that can be searched by meaning rather than by exact file names or keywords alone. Through this process, RAG allows foundation models to see and hear specific data points within a vast database. Instead of expecting the model to memorize every detail of a multimodal corpus, the RAG system selectively feeds the model only the most relevant snippets, frames, passages, clips, or cases required for a specific reasoning task. This makes inference more streamlined, more context-aware, and better aligned with the user's actual question. Internal knowledge and external multimodal evidence. Foundation models possess extensive internal knowledge, which is a static repository of information encoded within billions of parameters during pre-training. This internal knowledge gives the model broad familiarity with language, visual concepts, patterns, and general world knowledge. However, it is often fixed in time and lacks the granularity required for specific, data-intensive, or domain-sensitive tasks. Multimodal AI can recognize general categories and relationships, but it may not know the private, current, or case-specific details needed for a reliable answer. RAG alleviates this limitation by providing external context drawn from a multimodal database, including text, audio, video, and image data. This external context grounds the AI's reasoning in the actual data being managed and analyzed. In medical imaging or radiology, for instance, a model might use its internal knowledge of anatomy while relying on RAG to retrieve specific, similar cases from a multimodal database. The retrieved scans, reports, or case notes can then support a grounded and evidenced interpretation of a new scan. This distinction transforms the model from a generalist into a specialized agent capable of reasoning over private, current, or highly dynamic datasets. Limitations of standard RAG in multimodal AI. Although RAG enhances multimodal AI, the conventional or standard RAG approach has significant limitations. These limitations become more serious when the retrieved evidence includes not only text, but also images, audio, and video, because multimodal data can be larger, noisier, and harder to compare than ordinary text passages. First, standard RAG faces context window bottlenecks. Although powerful AI models can handle many tokens, filling the context window with too many retrieved chunks, sometimes called context stuffing, can increase noise, degrade reasoning performance, and increase latency and cost. The lost-in-the-middle phenomenon is also relevant. Models often forget or underuse information buried in the center of a large prompt. In multimodal AI, this problem can be even more complex because retrieved evidence may include transcripts, image descriptions, screenshots, frames, or multiple related clips. More context does not automatically mean better reasoning. The system must retrieve and present the most useful evidence. Second, standard RAG is limited by textual dominance. The internal space where multimodal large language models, LMMs, store information is overwhelmingly biased toward text. Even when processing images, the model's neurons may focus mostly on linguistic concepts. This can suppress the fine-grained visual details necessary to distinguish one image from another during retrieval. For multimodal AI, this is a major issue because the difference between two images, scans, diagrams, or video frames may be subtle but important. Third, standard RAG can fall into the alignment trap. LMMs spend much of their computational energy trying to bridge the gap between images and text by making different modalities speak the same representational language. This is very useful for generating captions or general descriptions, but it can also homogenize embeddings. As a result, different images may begin to look mathematically similar to the model, reducing the discriminative power needed to pick the exact right match from a list. In multimodal RAG, the goal is not merely to align images and text broadly. The system must preserve enough modality-specific detail to retrieve the precise evidence needed for the task. The rise of agentic RAG for multimodal AI. To overcome these limitations, the industry is shifting toward agentic architectures. Agentic RAG is characterized by autonomous decision-making and goal-oriented behavior. Unlike older RAG systems, which often follow a rigid and linear sequence of fetching information and then generating an answer, agentic RAG behaves more like a reasoning-capable assistant that can dynamically plan its approach. This is particularly valuable for multimodal AI because complex multimodal questions often require more than one retrieval step, more than one data source, and more than one type of analysis. Key characteristics of agentic RAG include the ability to break complex queries into subtasks, use diverse tools, and iteratively refine results until a sufficient answer is reached. These tools may include web search, structured databases, vector stores, specialized APIs, or external services connected through mechanisms such as the Model Context Protocol, MCP. In a multimodal AI system, an agent might first retrieve a transcript, then locate the corresponding video segment, then compare visual frames, then query a structured database for metadata, and finally synthesize the evidence into a coherent response. Naive or standard RAG paradigms rely on static, one-shot retrieval. If the initial search fails to find the right information, the system may produce an incomplete or hallucinated response. Agentic RAG uses planning and routing to decompose complex queries into smaller subtasks. It can decide in real time whether to query a structured SQL database, a vector database, or a live web search tool based on the specific needs of the prompt. For multimodal AI, this flexibility is crucial because the best evidence may not be stored in a single format or location. Re-ranking, reflection, and fallback strategies. Agentic RAG also helps address the garbage in, garbage out problem by implementing re-ranking. Instead of relying only on the top K-vector search results, the system can generate or compare multiple candidate answers from diverse contexts and use a specialized ranking agent to evaluate which response is most accurate. In multimodal AI, re-ranking can help determine whether a retrieved image, audio clip, video segment, or text passage truly supports the user's query. Agentic RAG also expands beyond a static knowledge base. If a document index lacks current data, the agent can identify the gap and autonomously decide to use a web search tool or live API to supplement its context. Even more importantly, Agentic RAG introduces reflection, allowing the system to check its own work. If a retrieved chunk is irrelevant, if an image match is too generic, if a video segment does not actually show the requested event, or if a tool call fails, a fallback agent can switch strategies midstream. This level of flexibility is difficult for traditional sequential pipelines to achieve. Conclusion: RAG makes multimodal AI more grounded and useful. RAG enhances multimodal AI by connecting the model's general reasoning ability with specific evidence from text, images, audio, video, and other data sources. It helps overcome the limitations of static parametric memory by supplying external context that is current, verifiable, and domain-specific. It also changes the role of data management. Databases and repositories are no longer passive archives, but active semantic retrieval layers that support multimodal reasoning. As multimodal AI becomes more common in fields such as medicine, education, research, compliance, media analysis, and enterprise knowledge work, RAG will be one of the key mechanisms that allows these systems to move from general generation toward grounded, evidence-based interpretation. If you find this information helpful, please like and share. And please feel free to drop your comments here. Thank you for watching.